I am Dr. Khalid Amin Khan from Oil and Gas Development Company, Pakistan. Our main author is Sana Kiani, along with other co-authors from Quaid-e-Azam University, Islamabad. The title of our presentation is Workflow for Computation of Geotechnical and Earthquake Engineering Parameters from Seismic Refraction and Uphole Logging. In this presentation, I will discuss a number of engineering parameters that can be computed from seismic-derived near-surface velocities. This is the outline of this presentation. We start with the objectives of the study, then a little introduction about refraction method, followed by discussion on the overall workflow for computation of engineering parameters. Since the working of the workflow is demonstrated through a case study, therefore some details about the study area and the key survey parameters are discussed. This is followed by presentation of various parameters that have been computed during different stages of the workflow. And finally, we have our conclusions. The main objectives of this study are to develop an efficient workflow for computation of a number of geotechnical and earthquake engineering parameters from near-surface compressional velocity model derived from seismic refraction or uphole logging surveys, and instantly generate maps highlighting the spatial distribution of the computed parameters that are helpful in site characterization and quick engineering decisions. Now let's have a brief introduction of seismic refraction and uphole logging techniques. We know that seismic refraction and uphole logging surveys are commonly carried out to delineate the thickness and compressional velocity of near-surface layers. In the petroleum industry, this near-surface information is used to compute static corrections, which are then applied to seismic reflection data. In addition, this information is also used to compute the shear wave velocity and subsequently a number of geotechnical and earthquake engineering parameters that are helpful in site characterization for civil engineering works. There has also been an increased trend of using multi-channel analysis of surface waves technique for estimation of shear wave velocity. This is our complete computational workflow. We start with automated first break picking from seismic refraction as well as uphole logging survey data. Then the travel time inversion is applied to the pick arrival times to delineate the near surface layers and their compressional velocities. This compressional velocity is used to compute density as well as shear wave velocity. Then we compute the average shear wave velocity of the top 30 meters of soil, which is required in most of the engineering applications. Once we have the density as well as compressional and shear wave velocity information, we can compute all the elastic moduli such as bulk modulus, shear modulus, Young's modulus, Poisson's ratio, and VPVS ratio. Next, we compute some geotechnical properties like allowable bearing pressure and standard penetration test. And finally, we compute earthquake engineering properties such as soil fundamental period, soil amplification factor, average horizontal spectral amplification for weak and strong motion, and finally seismic site characterization based on some building codes. The workflow has been applied to a study area of 100 square kilometers in the surroundings of Jund city, located about 135 kilometers west of Islamabad. The area lies in the western part of North Potwar deformed zone in Potwar sub-basin and has an undulating topography ranging between 250 to 450 meters. Uphole logging has been carried out at 60 points. The geophone offset is 2 meters and the hole depth is 70 meters, with 20 shots at different depth intervals. Reflection survey has also been carried out at 25 points, each having a spread length of 250 meters. The exposed formations in the area are comprised of sandstone and layers of silt and claystone. The topmost part of these formations has been weathered into loose soil. Now these are the sample seismic records from seismic refraction and uphole logging with automated first break picking. This is a 3D display of seismic amplitudes with the prominent first breaks. And this is a sample time distance graph of the picked arrival times. The inversion of these arrival times provides the thickness and velocities of near-surface layers. After complete processing of refraction and uphole logging data for the whole survey area, this is the resultant 3D visualization of near surface. At the top we have a 3D surface of the topography. Below it we have the spatial distribution of weathered layer thickness, and then we have the color maps of compressional velocities of weathered and subweathered layers. We know from rock physics that shear velocity can be computed from compressional velocity using Castagna's equations. However, these equations are not valid for near-surface unconsolidated rocks where the velocities are much lower. If the compressional velocity is lower than 1360 meters per second, Castagna equation gives a negative shear wave velocity. For near-surface unconsolidated rocks, a number of researchers have presented empirical relations between compressional and shear velocities. Based on the data from various researchers, Lee has presented two empirical relations for unconsolidated rocks. The first equation is applicable when shear wave velocity is greater than 1000 meters per second, while the second equation is valid when shear wave velocity is less than 1000 meters per second. We will be using these equations to compute shear wave velocity from compressional velocity. Using the Lee's equations, shear wave velocities have been computed from compressional wave velocities that were derived from seismic refraction and uphole logging data. The contour map on the left side shows shear wave velocity variations in the top weathered layer, while the contour map on the right side shows shear wave velocity variations in the subweathered layer. Now we need to compute the average shear wave velocity of the top 30 meters of soil, as it is required in most of the geotechnical applications. In addition, the National Earthquake Hazard Reduction Program and the Uniform Building Code also use the top 30 meters average shear wave velocity for site characterization. If we consider a two-layer near-surface model, then this is the top 30 meters and the average shear wave velocity for this 30-meter zone is given by this equation. This is the contour map of the average shear wave velocity of the top 30 meters of soil. As we can see, the average shear wave velocity is lower in the southeast and increases as we move towards the northwest. The velocity information is also used to compute density. On the left side, we have the contour map of density for the weathered layer, computed from compressional velocity using Gardner's equation. And on the right side, we have the contour map of porosity, which is derived from density. It is important to note from the color bars that the density and porosity are inversely proportional to each other. After computing the shear wave velocity and density from the compressional velocity, we can compute various elastic moduli such as bulk modulus, shear modulus, and Young modulus. These moduli are indicators of soil strength in bearing the overburden load. Similarly, we have other elastic parameters such as Poisson's ratio and BPVS ratio. Soil, when stressed due to loading, tends to deform. Bearing capacity is the capacity of the soil to support the loads applied to the ground. It is the maximum average contact pressure between the foundation and the soil which should not produce shear failure in the soil. Allowable bearing pressure is the ultimate bearing capacity divided by some factor of safety. It is computed by the given relation. This is the color map of allowable bearing pressure for the study area. It indicates that the eastern region has much lower bearing capacity as compared to the western region. The next parameter is soil amplification factor. The increase of amplitudes in soft sediments is one of the most important factors responsible for the amplification of earthquake motions. Soil amplification is a phenomenon observed in many earthquakes where the strength of the shaking increases abnormally in areas where shallow geologic layers have low seismic velocity. Soil amplification factor is computed from VS30, that is the average shear wave velocity of the top 30 meters, using the given empirical relation. This is the color map of soil amplification factor for the study area. It indicates that this pink region is highly unstable as it has the highest soil amplification factor. In general, the southeastern region has a higher soil amplification factor, which decreases as we move towards the northwest. It has been observed that destructive earthquakes show a correlation between damage and local geology, where the destruction is generally larger on soft soils as compared to hard soils. There is also evidence that the characteristics of ground shaking can be modified by the local soil conditions, and therefore long-period buildings located in areas having softer or deeper soils undergo more damage and collapse. As earthquake waves propagate through the soil media, their amplification or attenuation is mainly dependent on soil fundamental natural period, which is given by this relation. The color map of soil fundamental period shows that the pink region has the longest period and therefore is more vulnerable to earthquake damage. The trend of this map is similar to that of the soil amplification factor. The seismic response of the soil could induce amplification factors on the lodes, and therefore subsurface soil layers play an important role in ground shaking damages. This amplification is widely used for seismic microzonation studies. Average horizontal spectral amplification is defined as the ratio of the average horizontal spectral values of the rock to the surface in the period range of 0.4 to 2 seconds. It has been observed that the spectral shape and amplification is quite different during the main shock, that is the strong motion, and the aftershock, that is the weak motion. The average horizontal spectral amplification in the period range of 0.4 to 2 seconds for weak and strong motion are given by these relations. It can be seen that these parameters are related to 30 meters average shear wave velocity. The color map shows the average horizontal spectral amplification for strong motion. Here again the pink region has the highest amplification factor, and its trend is almost similar to the previous two maps for soil amplification factor and soil fundamental period. Standard penetration test has historically been the most widely used in situ dynamic penetration test designed to provide information on the geotechnical engineering properties of soil. The main purpose of this test is to provide an indication of the relative density of granular deposits, such as sands and gravels, for which it is virtually impossible to obtain undisturbed samples. Standard penetration test is generally performed through a mechanical setup as shown in the figure. A hollow cylinder along with some weight is dropped from a given height, and the number of blows are counted when it penetrates 1 meter into the soil. Thus, for soft soils, the blow count will be less as compared to hard soils. This test takes a lot of time and energy, but using geophysical engineering techniques, this parameter can be computed from shear wave velocity using the given empirical relation. The color map of standard penetration test shows that the western region of the study area is more suitable for construction of an industrial zone. The National Earthquake Hazard Reduction Program has developed soil classes based on average shear wave velocity of top 30 meters of soil. As can be seen in the table, soil class A represents the most stable region, while class E represents the most unstable region for civil engineering works. The study area has been characterized using this classification. The site characterization map indicates that all the red regions, mostly towards east and south, are not suitable for construction of an industrial zone. On the other hand, the blue and green regions are recommended for construction of any industrial site. From this study, it is concluded that geophysical methods are efficient and cost-effective as compared to geotechnical methods. Geophysical surveys can provide good estimates of near-surface engineering properties when implemented with care, keeping in view the local conditions. These techniques can solve challenging problems for civil engineering works that cannot be faced through the classical geotechnical methods. Thank you.